So here's a slightly modified version of the language processing model, I believe, figure 1.3 in Murray and Clark. And I've simplified it. For example, we don't see morphosyntactic processor here. We don't see non-language processes such as object recognition. So the idea here is to pare it down a little bit, make it a little bit more digestible. Also, you can see I've written some words near each processor, and we're going to go through briefly, talk about each processor, and really what I'm going to do is I'm going to talk about the processors more in terms of how we might think about these processes when we're doing assessment, right? So one basic thing I think to notice here is that there's, in a sense, a dividing line, right? Where everything here is input and everything here is output. So here we have speech and reading as our language inputs. And on the other side, we have speech and writing as our language outputs. The other thing to notice is that the semantic system is at the center, and that both the inputs and the outputs rely on the same semantic system. Now, with just making that statement, right? So models of language that propose that there is one semantic system. It is shared between inputs and outputs, and let's say it's even shared across different modalities of information processing. One of the things that we would have to assume is that, let's say, our semantic system, we had a patient who had moderate to severe semantic impairment. And that was it. No other damage in any of these other processors. Well, based on this model, we should see a certain kind of pattern, right? And we should say that they will have moderate to severe reading problems. They will have moderate to severe difficulty with auditory comprehension. They will have moderate to severe difficulty expressing themselves. And they will have moderate to severe difficulty writing. So we have equal amounts of impairment across all of the modalities that share this important central processor, right? If we were to say that the semantic system was mildly impaired, then all of these would change to mild, right? And we might see other things, such as similar kinds of errors being made, semantically based errors, primarily being what we would expect to see. So let's talk about these processors, and we'll start the input side. So speech. We hear someone speaking to us. The first thing we do is we get into the phonological processing system, where we start to discriminate the different speech sounds, right? And a simple task that we use to determine how good people are at parsing out speech sounds and discriminating speech sounds is to do something like a minimal pairs task, right? So here, fan and van, probably the hardest type of minimal pairs task, right? Because these two, F and V, only differ by one distinctive feature, right? Distinctive. If we were to do fan and ban, that is an easier distinction to make. And so with patients who have problems here, and if they're severe, we may have to try tasks that have two distinctive features before we get some accuracy, right? So we can, by using distinctive features, we can play with the difficulty of the task. Let's say they hear the sounds correctly, right? And they hear the order of the sounds, F, F, E, N. Okay? They hear that. They hear the order. Now, the next thing is to match that heard word with a word that you already have stored in your mental dictionary, a memory, so to speak, because you've heard that word before. You have heard fan before, so you recognize, aha, that is a word in my language. We can test this processor by doing what we call an auditory lexical decision-making task. Where we give people real words and non-words. And all they have to do is just say, yes, this is a real word, or no, it is not a real word. All the non-words that we give them have to be what we would call phonotactic, referring to sounds, phonotactically legal. In other words, it has to be a type of sound combination that we could see in the English language. So here, a person would say, you would say hen, and they would say, no, that's not a real word. You say car, yes, that's a real word. Now, the interesting thing is that you can do well at this task, even if your access to your semantic system is completely destroyed, okay? And personally, we have experiences something like this, right? So for example, you'll hear somebody say a word, you'll be reading and you'll read a word, you don't know what it means, but you know you've seen it before, okay? So that's kind of a lay experience for this sense of you have a word stored in your phonological input lexicon because you've been exposed to it sometime in the past, but for whatever reason your exposure wasn't strong enough so that you also had a nice hearty definition, semantic information associated with that. This task, auditory or the phonological input lexicon, is sensitive to frequency. Right? So what I mean by that is that what will determine how easy or hard this task is for a patient with aphasia will be how common the words are that we give them to make a decision about, right? And that makes sense, right? Because this input lexicon is based on previous exposure. The more times you've been exposed to the word car, the more solid that representation is in your mental dictionary. The word anosognosia you may or may not have been exposed to, depending on which speech pathology classes you've taken before. And so that word is not as heartily established. So what we will tend to see in people with aphasia is that there will be a frequency effect in their understanding of words, that they'll understand words more easily the more common the words are. Let's move over to the other input, reading. And we'll start with this peripheral analysis, abstract letter identification. Think about this. You know a G represents a G in your language, whether it's written in uppercase or lowercase. even though, as the example here shows, a small g and a big G don't look that similar, right? In other words, you have abstract. You know what, these two visual figures represent some abstract knowledge. In this case, the sound g, right? Similarly, when you think about it, we have to read text that's written in all kinds of different fonts, etc. It's printed, sometimes it's cursive, etc. Okay, so that's our first level of processing. Once we've done abstract letter identification and we've kind of seen the word as a whole, we go into we match this string of identified letters with a lexical item that we've already been exposed to in the past. So notice here that according to this model, we have two separate lexicons. We've got a lexicon for heard words, in a sense a mental dictionary for heard words, and a lexicon for written words. Why do we have these different lexicons? We have these different lexicons because basically in the past there have been cases of individuals where one was damaged and the other wasn't. And so this kind of isolated damage was enough to suggest that there are two separate types of lexicons. Now, there are other models of language processing that say no, there isn't separate lexicons, and we have an argument for how you can get isolated damage to, let's say, orthography. Okay, but we're not going to go that deep in this class. If anybody's interested, I can point you in the right direction, reading-wise. So here in the orthographic input lexicon, we're doing the same thing. We're recognizing whether words are real or not, whether they exist in our mental dictionary or not. Notice here, this word care, right? It's called pseudo-homophone, which is a non-word, which is pronounced the same as a real word. Okay. A homophone would be two words that are spelled differently. They're both real words, and they sound the same. Okay. One thing about this orthographic input lexicon is that it also reflects the fact that we have two roots for reading, right? When we learn to read, we do what we would call grapheme to phoneme conversion. A grapheme is a letter that represents a sound in the English language. So, T, that letter equals the T sound, right? That's a grapheme. But graphemes can be more than one letter long. TH still only represents one sound. So that is that both of these are graphemes. They are 1 to 2 letter combinations that equal one sound. In the beginning, we read through grapheme to phoneme conversion. And so you can read care, or you can read another non-word like trimpy. Because you can go through an alternate route. You can just take the letter to sound rules is what I've just been talking about, grapheme to phoneme conversion. So you would be able to read words like ziz and trimpy out loud correctly if this root was working adequately. Okay. Sometimes we'll see patients with reading problems where they have a disproportionate difficulty reading irregularly spelled words. Kernel. Kernel is an irregularly spelled word. It's not pronounced the way it's spelled, right? It should be pronounced colonel. If the orthographic input lexicon is damaged, then when you see this word, you have no other choice but to go through this sound it out route, in which case you will read it out loud as colonel. Okay? Because the orthographic input lexicon has these memory of words, right? It can say, oh, I recognize that word and I know how it's pronounced. When most of us rely on this whole word route to read, right? We sight read. But if we run across a word that we've never seen before, or we're faced with pronouncing someone's last name and they're maybe from a culture that we're not familiar with, then we have to rely on these letter to sound rules. Both the phonological input lexicon and orthographic input lexicon, once we recognize these real heard or spoken words in our language, the next thing that we have to do is that we have to find the precise semantic representation that matches kernel, right? And there's a match. So now we've got the whole shebang, don't we? We know what the word is, how it's pronounced, and what it means. Okay? So we can break down here, right? We can have people who do fine, but they have trouble linking the word to its semantic representation. Or we can have damage in the semantic system itself. Remember, I said that these lexicons are, because they're so much based on exposure, they're very sensitive to frequency. High frequency words easier to process for these processors, low frequency words more challenging. The semantic system is more sensitive to imageability. Words that are very imageable have more potent semantic representations. If you think about the word fire, right? The word fire, you can see it. You can conjure up a lot more in your mind's eye than you can with the word heat. So fire has high imageability and heat has low imageability. How do we get imageability ratings? Well, the way researchers do it is they get normal subjects, they give them a bunch of words and they say, okay, on a scale of 1 to 10, how easy can you see this word in your mind's eye? Fire. Oh, I give it a 7. I can see it quite vividly. Heat. Can't really see that. Maybe a 2. So far we've talked about hearing words, reading words. What if we want to produce something? What if we want to speak? Well, we would start here. Right? We start activating the concept that we want to talk about. And a semantic representation Has also You will also see the word conceptual memory being used. Conceptual memory. So we have to activate this concept, and then we have to find the symbol, i.e. the string of phonological elements in our phonological output lexicon that represents this semantic representation or concept. Once we've activated the phonological word form, the string of sounds that represents, let's say our concept is dog, then we have to hold these phonological elements. Here we don't have much to hold, do we? D, a, g. We have to hold it in a very short-term memory called a phonological buffer, long enough for all the motor planning to be done to transform this abstract linguistic phonemic code into a motor act. Now, backing up a little bit, just like the input lexicons, the output lexicons are sensitive to frequency. So when a person has damage to the phonological output lexicon, we tend to see them doing much, much better naming objects that are high frequency, or being able to say words that are high frequency versus low frequency. So man is a very common word, obturator, much less common. Okay. At this level, length doesn't really play a role. Length doesn't play a role. This is all about how often you've used the word. Right? The more often you've used the word, the more you've retrieved that word from your mental dictionary, the easier it will be for you to do so in the future, even in the context of some brain damage. Length does play a role in the buffer, right? The holding of these phonological elements long enough to do the motor planning and motor execution. So in this damage here, you would expect a person to do much better with short words than with long words, right? Because this is more to hold in memory, so to speak. Here, on the orthographic output side, we also have frequency effects, okay? But we also have regularity effects, right? So in other words, yacht, both yacht and pint are not pronounced exactly the way they sound. So for example, if you were to, a patient with damage here, if you were to ask them, spell the word yacht, they might do something like this. Yacht. Okay. Because they haven't been able to retrieve that stored whole word representation. What they've had to do is, mentally, they've had to do a acoustic to phonological conversion, right? In other words, they've had to they hear what you say, they hold that phonological information in their mind in the buffer, then they say yeah, they do their letter to sound rule conversion here, so they say to themselves y, ah. I think that would be ah, t, right? And then they send it to the buffer for the motor planning to write it out. Yacht. This acoustic to phonological conversion allows us is a simple little side process that explains how people can repeat words that aren't real, right? If we didn't have this, the phonological input lexicon just stores real words. So if you gave a person, they heard, remember this is the input side, they heard Trimpy, they wouldn't find a match for it in their mental dictionary. They wouldn't be able to repeat it. Of course, we know people can do that. That's because they can do this simple acoustic to phonological conversion. Okay, so this is a brief tutorial on this model, how we kind of think about it in terms of testing, what kind of error patterns we might expect to see. There's a lot to learn here. I can tell you, just so you put things into perspective, I was not taught this model when I was in graduate school. I was probably a therapist about 5 years before I decided that I was going to learn more than the superficial stuff I had been taught in school at the time. And once I started reading the psycholinguistic literature, so this model is sometimes called a psycholinguistic model. Other people have called the model and the way of thinking about language is being processed in steps like this as a cognitive neuropsychological model. Once I started to do this reading, it took me about 5 years before I felt really comfortable manipulating this information in real time during my assessments, etc. So if you feel a little overwhelmed, you should. That's just the way it goes. That being said, I think it's important to expose you to this model to give you an idea of kind of what to shoot for in your career if let's say you're going to be working with a population that has aphasia. I do definitely think that thinking this way can not only result in better treatment plans, but there's a level of confidence that we gain when we feel like we're able to think a little bit deeper about the underlying reasons why our patients have the symptoms that they have, a symptom being word finding difficulties, right? In this model, as you can see, people can have word finding difficulties because of problems at different junctures. Their semantic system is impaired, their phonological output lexicon is impaired, the phonological buffer is impaired. And so while this kind of model can take a while to get comfortable with, of course, even small baby steps towards utilizing this approach, I think will pays dividends, as long as we understand that it does take a while to get to a certain level of ease thinking in this way.